Good afternoon, everybody. Today I am going to tell you about a very important law, the third law of thermodynamics. As we all know that we have studied the first law of thermodynamics, the second law of thermodynamics. The first law of thermodynamics gave us the concept of energy content, the internal energy, the enthalpy of a system, and the second law of thermodynamics gave us the concept of entropy. So, if we see in this manner, the third law of thermodynamics, it does not give us any new concept. Moreover, the scientists are divided in their opinion over calling it as a law. But since it is based on generalizations which are based on experiences, so it gives some technical and scientific edge to it. So, it is known as the third law of thermodynamics. Now, before going to the third law of thermodynamics, we must discuss three things first of all. First is the entropy. Entropy, as we all know, is disorder or randomness in the system. Another thing is absolute zero. Actually, the concept of absolute zero has been introduced by this law only. And the third one is an idea of a perfect crystal. Idea of a perfect crystal. So let's talk about these 3 points first of all, and then we will eventually reach to what is the statement of the third law of thermodynamics. As we all know that entropy is disorder in a system. Suppose we are having a system, and if we supply heat to it, supply some heat to it, then what will happen? Suppose it is entropy, this is the initial entropy of the system, and we supply some heat to it, then what will happen? The system will now will be at another state, pressure, volume and temperature, and the entropy of the system will be S. Now we can calculate the change in the entropy, means SF minus SI will give us the change in the entropy. This we all have seen by studying the entropy as well as the second law of thermodynamics, that we can study the change in the entropy in this way. Now, when we are supplying some heat to the system, then randomness is increasing. The kinetic energy of the molecules is increasing, and so the disorder is increasing. Now, this means that if the disorder is increasing by increasing the temperature of the system, suppose we increase the temperature of the system, increase the temperature, what will happen? Disorder is increasing. Disorder is increasing in the system. This means if we decrease the temperature, we will be able to arrest the disorder. If we decrease the temperature of the system, we can easily stop the disorder of the system, and the substance will be ordered. Means we will increase the order in the system if we decrease the temperature. Because the kinetic energy will decrease. When we are decreasing the temperature, kinetic energy will decrease, and the molecular vibrations will decrease, and eventually we can attain a point when the kinetic energy is zero. So, as we all know that kinetic energy is in fact, we all know this, that 3/2 RT, R is nothing but gas constant. Now, suppose the kinetic energy is zero, this means that 3/2 cannot be zero. R is a gas constant, and we know it is not equal to zero. This means T should be equal to zero. This T should be equal to zero. And here comes the concept of absolute temperature. And this is nothing but zero Kelvins. Or we can say it is, if we talk about degree centigrades, it is minus 273.15 degrees centigrades. So T is actually minus 273.15 degrees centigrades, which is nothing but 0 Kelvins. So 0 Kelvins is equivalent to minus 273.15 degrees centigrades. This means that at absolute zero, a substance will be perfectly ordered, a perfectly crystalline solid substance will have zero entropy at absolute zero. Means that if we are able to attain a temperature of absolute zero, then the entropy will be zero. And this very statement is the statement of the third law of thermodynamics. Here I would like to clear two things. But before that, let me clear the statement of thermodynamics once again, that every perfect crystalline substance at absolute temperature will have zero entropy. Now there are two things. First is that it is not possible to attain a temperature of 0 kelvins, and it is only an ideal concept that 0 Kelvin exists. And moreover, another thing which I want to make it clear here is that we cannot calculate the absolute entropy of any substance. We can calculate only a change in entropy. Absolute entropy can not be calculated. So here, how can we calculate the absolute entropy of a substance? Here the third law of thermodynamics comes into rescue. So with the help of third law of thermodynamics and with the help of this statement that a perfectly crystalline substance will have zero entropy at absolute zero. With the help of this statement, we can calculate the absolute entropies of solid, liquid or the gas. Now as I have told you that the entropy will be zero at absolute zero, and the crystal will be a perfect crystal. Now here I would like to tell you that this statement is not considered to be a perfect, that every perfect crystalline substance will have a zero entropy. Instead of this, what we consider is that the entropy of all the perfect crystalline substances at absolute temperature is considered to be equal. So in fact this is also another alternative way of expressing the third law of thermodynamics. Now let's see, just one more thing I want to make it clear, that when we talk about a perfectly ordered crystal, so the idea of a perfectly ordered crystal is also an ideal statement, because no crystal is 100% perfect, and when a crystal is never 100% perfect, there always remains a room for entropy, for disorder. So these things are only ideal, and in normal way they do not exist. In a practical way they do not exist. Now how can we calculate the absolute entropy of a liquid or a gas with the help of the third law of thermodynamics? For that, thermodynamics. Here I would like to clear two things. But before that, let me clear the statement of thermodynamics once again, that every perfect crystalline substance at absolute temperature will have zero entropy. Now there are two things. First is that it is not possible to attain a temperature of 0 kelvins, and it is only an ideal concept that 0 Kelvin exists. And moreover, another thing which I want to make it clear here is that we cannot calculate the absolute entropy of any substance. We can calculate only a change in entropy. Absolute entropy can not be calculated. So here, how can we calculate the absolute entropy of a substance? Here the third law of thermodynamics comes into rescue. So with the help of third law of thermodynamics and with the help of this statement that a perfectly crystalline substance will have zero entropy at absolute zero, with the help of this statement we can calculate the absolute entropies of solid, liquid or the gas. Now as I have told you that the entropy will be zero at absolute zero, and the crystal will be a perfect crystal. Now here I would like to tell you that this statement is not considered to be a perfect, that every perfect crystalline substance will have a zero entropy. Instead of this, what we consider is that the entropy of all the perfect crystalline substances at absolute temperature is considered to be equal. So in fact this is also another alternative way of expressing the third law of thermodynamics. Now let's see, just one more thing I want to make it clear, that when we talk about a perfectly ordered crystal, so the idea of a perfectly ordered crystal is also an ideal statement, because no crystal is 100% perfect, and when a crystal is never 100% perfect, there always remains a room for entropy, for disorder. So these things are only ideal, and in normal way they do not exist, in a practical way they do not exist. Now how can we calculate the absolute entropy of a liquid or a gas? So now let us assume a system which is at 0 Kelvin, and we are supplying heat to it, and when we are supplying heat to it, suppose the temperature that is attained is T Kelvin, and the entropy increases from 0 to St. 0 is the entropy at when the temperature is 0 Kelvin. So the change in entropy we can determine by entropy, final entropy minus the initial entropy, which is St minus S. And now applying the third law of thermodynamics, we know that the entropy at absolute 0 of perfectly crystalline substance is 0. So this factor will be 0, and when this is 0, then the change in entropy will give us St. St is the absolute entropy at temperature, at any temperature at which we are calculating. So the change in entropy is given by St. So utilizing this thing, we can calculate the absolute entropy of a substance. We will calculate the change in the entropy, and then we can calculate what will be the absolute entropy. Now how will we calculate the change in entropy? For that, as we know from the entropy definition also, that ds is equal to dq upon t. ds is equal to dq upon t. This is one of the mathematical formulation for entropy. Here ds is a very small change in the entropy, means infinitesimal change, increase in the entropy is given by ds. Now if we have to calculate the whole change in the entropy, we will sum all these ds parts and we will get the total change in the entropy. So when ds is equal to dq upon t, let us assume it to be equation number 1. And now from the definition of the heat capacities at constant pressure, it is given by dq upon dt. The heat capacity at constant pressure is given by dq upon dt. So this dq will be equal to Cp multiplied by dt. We will cross multiply and get the value of dq. Substituting this value of dq in equation number 1, we find that finally we will get ds is equal to Cp dt upon t. Okay, dq is actually Cp dt. So ds will be equal to Cp dt upon t. Let it be equation number 3. Now, just now I have told you that when we will sum up all these ds quantities from temperature 0 to temperature T, then we will get integrate it to limit 0 and T, and we will get in this way equation number 4. Here also in the limits 0 to T, and we will get this equation number 4. And now when we will solve it between limits 0 and T, we will get St minus S0 is equal to Cp T log natural T. Log natural T is nothing but 2.303 log of T. So as we know that S0 is 0, so St will be equal to Cp T log natural T. So in this way, by knowing the values of Cp at different temperatures, by plotting them on a curve and by calculating the area under this curve, we can calculate the absolute entropy of the substance. By calculating the values of the heat capacities at constant pressure, by plotting these values at different temperatures, we can get a curve like this. So this is the curve when we plot the values of Cp against log T, we get a curve like this. And so the area under this curve will give us the value of the heat of absolute entropy. But this is not sufficient, because after below 15 kelvins, below temperature of 15 kelvins, we do not get accurate values of Cp. Means Cp values cannot be calculated below temperature of 15 Kelvin. So what we get is this much graph. So what we will do is extrapolate this graph to this 0 Kelvins. We will extrapolate it so that we can get the values till T is equal to 0 Kelvins. So we will calculate the area under this curve. This will give us the absolute entropy, but up to only 15 kelvins. Let it be T1. Let it be T1. Let this point B be equal to T1. So we can get the absolute values of entropy Cp, TL and T by calculating the area under this curve. And to calculate the area for this, we use a law which is known as divide T cubed law. It is divide T cubed law. So when we are calculating the whole this area, we are having two parts of this integral. One is the area under 0 to T1, which is shown by this part of the graph. This area under this graph, under this curve, and plus from T to T1, which is the area under this curve. When we plus both these areas, we will get the total change in the entropy. Solid substances, we have seen that we have two integral parts. One is for 0 Kelvin to T1, which is usually 15 kelvins, and another one is from T1 to the desired temperature. But this is valid only for the solids which do not show polymorphism. And suppose they show polymorphism, then the heat of transition will also come into play, and then entropy change delta H T upon T will also have to be included in calculation of the entropy changes. Now for the liquids and the gaseous states, the entropy change starting from T is equal to 0 Kelvin to the desired temperature of the liquid, all the entropy changes which are involved in all the stages have to be taken into consideration. Let me explain it for gaseous state here. Suppose you have to calculate the entropy of a gas at 25 degrees centigrade, then what will be the major steps in it? So the first step will be the entropy of heating the crystalline substance from 0 kelvins to how much? To its fusion point. So 0 kelvins to fusion point, and this will be the formula that is to be used. And as we have seen just now, that it is actually the sum of these two integrals, 1 upon 3 Cp at T1, which we have derived from the divide dt cube law, and this is for the temperature between T1 to the fusion temperature. Means when that solid changes to the that ice changes to the water. We are taking here, suppose we take the example of ice vapor. And so the ice melts, so we have T1 to Tf. So we take this into consideration. Then there is the entropy of fusion to be considered, which is actually delta Hf upon Tf, where delta Hf is the heat of fusion, and at the fusion temperature Tf. Then there is the entropy of heating the liquid. We have got the liquid here after the fusion, and then we have to calculate the entropy of heating the liquid, means from fusion temperature to the boiling point. And the entropy change here will be given by this integral. Then once we are having a boiling liquid, we have to consider the entropy of vaporization also now, which will be delta Hv upon Tv. where, as we all know, that delta Hp is the heat of vaporization and Tb is the boiling temperature. Another thing which we have to consider is the entropy of heating that gas to from Tb, the boiling point of that liquid, to 25 degrees centigrade, which is 298 kelvins. 298 kelvins. We are having 298 kelvins. We are having this integral part. Cp of the gaseous system. Step number 1, 2, 3, 4, 5. All these steps put together will give the entropy of a gas at 25 degrees centigrade. And suppose we are considering only the solid, then the first step will be taken into consideration from 0 to Tf along with the heat. And if we are taking the liquid, then these 3 steps need to be taken into consideration. Moreover, the first step will be the sum of these two integrals from 0 to 15 degrees, 15 Kelvin, and from 15 Kelvin to Tf. For that we use the divide d block, as I have told you just now. And so, just have a look at this graph which shows the entropy change with the rise of temperature. Suppose this is the increase in the entropy, and here we are having the temperature. Now this graph will start from here at T is equal to 0 Kelvin. Suppose this graph is not starting from T is equal to 0, then it means that it is not a perfectly ordered crystal. So from T is equal to 0, when we are supplying heat to it, it comes to this point. Suppose it is the water, ice, liquid, and the gaseous. For that we have, suppose this graph stands for that, then at 273 Kelvin, all the ice will melt into liquid. And then again, there will not much change in the temperature, there will be too much change in the entropy, because this ice is changing to the liquid form. Means the solid is changing to the liquid at fixed temperature of 273 Kelvin, which is 0 degrees centigrade. So this will give us the entropy of fusion. Entropy of fusion, this thing, will be equal to entropy of fusion. And at this point, when we supply more heat to it, the liquid, the whole of the ice will change to the liquid form, and at this 373 Kelvin means 100 degrees centigrade. All the liquid will start vaporizing at this point, and this signifies this portion, signifies the entropy of vaporization S. This one, it signifies the entropy of vaporization, and then we get the vapor state, the gaseous state. So this is a whole graph just to depict the entropy change with the rise of temperature. So today I have told you about this third law of thermodynamics. From the third law of thermodynamics, we got introduced to the concept of absolute entropy and how to calculate the absolute entropy using the statement of the third law of thermodynamics, and we have also got the concept of absolute zero. Though absolute zero and absolute entropy of substance are only ideal and they do not exist as such, but only for the study, experimental study. We do it like this, though these things are theoretical. That's all. Thank you.